好像一路都结束为止，就是练习运动到。那等下就是如果他开始张飞写的时候，就会把它写过去。
Okay, we're going to test throws three. Be on the rock.
Oh, set. Okay. Okay, you land on the threshold.
其他就这么看的，这么看就好。谢谢。
The recorder, please get onto the stage.
So, hello everyone, I'm the reporter Jim Stanley, and today we're going to report how they are doing on the rock. Here is the power station. Water on the vertical steel rod may start spinning instead of simply sliding down. Study the motion of water and investigate what determines the terminal velocity. And we dig, the main focus is study the motion of water and investigate what determines the terminal velocity. Here's the table of contents. First, we're going to talk about the study of motion and the terminal speed. Second, we're talking about the theory, and this includes the analysis of the variables. Three, we are going to talk about our experiment data. Four, we're going to conclude the whole report. And here is the study of motion. In a theoretical model, we found that there are two types of motion. The first kind of motion is a circular motion. The second kind of motion is a sliding motion. In 3D, the track is in a shape like a spiral. And the blue track is the track for the point mass of the ring. And what is terminal speed? When a moving object keeps its speed at a point where the acceleration equals to zero, this situation occurs when the object's resultant force turns to zero, according to Newton's first law. When a box situation happens, the object stays in its original velocity, or stays at the original state. In this experiment, terminal speed is all about sliding motion. And the last statement means that we're going to talk about terminal speed when the ring only stays on the z-axis. And here's the theory of the phenomenon. First, we will assume, as described on the previous page, the ring goes in circular motion on an xy plane. So first, we regard the ring as the point mass. So it is easier to model. The normal force provides a centrifugal force for circular motion of the point mass. And the radius can be written down like this because of the ring is assumed as a point mass and goes around the rod. So we can formulate this equation. And the next one, we're going to talk about the rod and the on the z-axis move in the sliding motion. So the contact point of friction is opposite of the curve itself. I mean, if we assume this is a rod and this is a ring around it, the contact point here has a friction opposite of the curve. And this formula can show the coefficient of the friction. And bringing the differential equation for the next formula, this equation can be found. So the relationship between angular with speed and time. And now, this page shows the predict result of our experiment from the theory. The final result we calculate is the terminal speed. And these are the steps that we calculate. And here are the data that we originally know, but we haven't tried it in the experiment. And why the mu equals to tangent 12.5? Because the way we know the coefficient of the friction is where we have a rod, and here's the table, and we will lift the rod, and until an angle, the ring will start to slide down, and that's why tangent 12.5 degrees equals to the coefficient of friction. And this is the radius of the ring, and the smaller r is the radius of the rod. And the theta is 27.5, and this means that the angle between the x-axis of the ring and the vertical axis, omega t is the omega t is the terminal speed for the terminal angular velocity, the angular frequency for the ring, and t is the time period, and this is the terminal speed. Okay, and here's the demonstration for the I'll show you again. Okay, from the last page, you can see, on this video, you can see that the ring before there's a strange way of moving on the graph. So this is the track data of motion of the ring. And the first stage here, and this is the same scale, so you can refer this time. Okay. So from an AC graph, you can see there's 5 stages of motion. First, the ring falls and spins at the same time quickly. So you can see the AC graph and also the velocity gets slow because of a ring colliding with the rocks, causing friction. So at the side, you spin the ring around the rock and starts to collide with the rock and causing a lot of friction. And this slows the sliding motion. So it decreases the velocity of sliding. And in the second stage, the ring starts to spin on the rock instead of falling. And when the second stage happens, it almost stays at the same velocity. And why there are sometimes that the velocity is below 0, because I think that's because the ring starts to collide and it bumps the ring upwards. And then the third stage, the ring starts to go in a super unstable motion. You can see here the velocity is super unpredictable, and there's even the ring even stuck on the rock. And from fourth, the ring starts to spin and fall at a steady speed. And you can see here why there is no little change in the velocity is because of maybe because of the colliding sensation of the ring and the rock. In the fourth stage, the ring just falls down at a normal condition, and only the gravitational force for the falling motion. And this line over here is the predict terminal velocity. And I think the reason between the predict velocity and the terminal velocity is because of extra fusion caused by before, like the extra colliding on the rod and the extra frictions. And here is our conclusion. First, we're going to talk about the flaws in our power experiment. The surface of the ring might be uneven, so the terminal speed is not correctly recorded. And this means that maybe our ring is not a complete circle, so that will cause extra friction or something. And the second, the rod might be vibrating, causing the ring to collide with the rod, causing extra friction affecting the motion. So, the explanation of the second point is when we are trying to experiment, I use my hand to try to hold the rod, because if I didn't do that, the rod will just fall over. And when I try to do this, I feel the vibrating of the ring, and I think that is a great factor of the result. So the third one, not enough experiment data. We only try this experiment once, and the one doesn't show much evidence for our theory. And the second, we're going to talk about theory flaws. Not detailed enough for complete studying the motion of water. For example, the shaking motion. This is about the vibrating of the rock. And now the experiment finding. We found that the changing of the velocity at stage 4 seems to have a cycle. Here, it seems to have a cycle of changing velocity. And then vibrating of the rod causes the data to be inaccurate. I talked about this a lot of times. The vibrating of rod might be a great factor for the result. And for the future outlook, try to organize the sample or change velocity as a finding. Consider the vibrating of the rod and the ring and formulate to correct the falling velocity data. So I think in the future we can try to model out the effect of the vibration of the rod, because I think vibration can be analysis and to correct the data. Okay. Thank you for listening.
It's time for the opponent to ask the questions.
So some questions for you. First is that, can you please change your experimental data page? And can I ask first the first terminal velocity?
Oh, here. It collided and this state, but I think this is
Okay, and the second one is, I want to ask the contact, do you have one contact point or two contact points? The rod and the ring.
Yeah. That's how I know. When I try the experiment, I hold my hand here, right? So I can see if the ring contact is on 1.2, and I think I only discovered one contact point.
Okay. And can you share your video again since I can see the ring?
Okay.
And since you say that the vibration will affect the result, and how do you think vibration will affect? How do you think the vibration will affect these parameters?
Oh, I think that the vibrating will cause this extra colliding of the between the ring and the rod, and that will cause energy loss, and that's one of the reasons why the predicted velocity and the terminal velocity are different. Yes.
And can you explain this later again? The upward.
Here, the
Yes.
SC graph.
Yeah.
Okay, so here, this is just a
So you define the top of the rod
Yes,
as
yes.
0. Okay.
Yes.
their main focus is the motion of the washer and the parameters that would affect the terminal velocity. And the summary of the report is that two types of 2D motion and a 3D model, and they define the terminal velocity. And they have the formula of the normal force, for example, the mass, the radius, or the angular velocity. And they have the relationship between the static friction and the coefficient of sliding friction. And for their setup, it's being down the rod and until it reaches this terminal velocity. And for reporters, our advantage is that they have good demonstration graphics, and it seems to be understand experiment well, and he explained the charts detail. So our suggestions is that they should have used the page number so we can discuss clearly. And some formulas are good, and so they could have improved in the future. And the experimental data could be more substantial. And instead of its advantages is that the starting process, the averages are clearly shown. And the suggestions is that we think they must have more parameters. For example, the radius of the rod or the ring. And they could have talked to you in a demonstration video and have more explanation about their capture angle. And they could have analyzed the characteristics of each apparatus. And about this theory, your advantage is that they have a clear definition of the formula, and then point out the key factor that affects the terminal velocity, which is the sliding. And our suggestions is that they should have a model of a 3D mode, of a 2D motion, I'm sorry, it's a typo. And they lack of a calculation of the sliding that affects. And the unit, which is the last, to be the same. And their advantages of the experiment is that they elaborate on the same graphic, and but they also have to figure out the clear theoretical value. And our suggestions is that the surface of the ring can within the surface of the ring can be replaced with the center of mass of the washer. And they should have more data to increase the accuracy. And further explanation of the boundary, which is the one that we provide. And here comes our discussion section. So please go to the next page. Okay. First of all is the phenomena of the theory page. I don't know which page is it. Oh, this. Yeah. Okay. And since you see that you only have one contact point, so you see that in this theory, this one find out the big R minus small r. Since if this one is the ring and this one is the rod, and although this is rotating, the distance between this and this will remain the same. So we think that it might only have a little r instead of big R minus small r.
But my explanation for this is that this is the radius of the ring, right? Whole radius, and this is the center of mass. And minus the little r, and this is we're gonna follow the point mass of the ring, so I think it goes around like this. So I think the radius will still be the big R minus the small r. Yes.
Okay, and the next page. Since you have said that you have a sliding friction, so I think it wouldn't be static friction. It should be kinetic friction. So I think this formula doesn't make sense.
I need to clarify. Why I use static friction because that the whole motion, the contact point is always moving. So it didn't have any drag motion between the ring and the rod, so I think it's still a static friction since that the points are still moving. One second is like this, and another second is like this.
But you say that you did consider the sliding. So are we still seeing that?
Oh yes. I forgot to say that. We forgot to formulate. This is the view of top right front. Here, the ring. So we forgot to consider this also.
And so since you say that you consider the sliding, and how do you think the sliding look at this experiment?
Sliding.
Yeah.
You mean the whole ring just slides down or spinning around it? Sliding.
The sliding one is spinning.
Sliding and spinning.
Oh, one is spinning.
Yes. Definitely. Both of these will decay the energy, the initial energy.
Okay, but as for the opponents, we're saying that it will affect the energy. And what do you think? Since it will, and what do you think that the energy will transform as?
I think because all the energy decays, it's all because of friction. So that means that maybe the friction will transform the energy to heat.
We have the sampling it so that the potential energy will transform into the friction. But since it is transforming, so we think that it's still the kinetic friction that it changes, instead of static friction.
Oh, so you mean, can you give a statement again?
That we think that it's the potential energy that transformed into the kinetic friction. So the potential energy will equal to the work that the kinetic friction has gone.
Okay. And can I ask you a question? What's the purpose of testing one contact point and two contact points? Because in our experiment we didn't seem to observe any kind of observation about two contact points. So can you draw a demonstration of the two contact points when this phenomenon happens?
Oh, so that is you can. I don't know that it's like this one. So you will have one on the top and one at the bottom. So there will be two contact points.
Also, but I think is there any limitation, like any situation when that happens, like the radius and the portion between the radius of the ring and the rod?
When the inclination angle is big, and they will have two contact points instead of one. Like the inclination angle is that this is the ring and this is rod, and this is the inclination angle.
Yes.
So when it's big, I think there will be two contact points.
Sorry, can I have a new marker?
And it's okay. We can keep discussing.
Okay.
And also in next week. And this formula, you define it.
I think that's about
The time or
the time. Yes, sir.
but so this is about the velocity. But if the t equals to time, the omega 0 wouldn't change and the CRR wouldn't change. So the whole formula will changes the t. But if this formula stands, there won't be a terminal angular velocity. So I think there might be something right here.
Also to correct, there's a result of the formula.
Yeah, so there must be something like that. So that's when. And also because you talk about a rolling resistance coefficient, and I want to ask you, what is the time when the rod drops from the top to the down? The bottom, the time to be that.
The time, you mean the time?
Yeah, it's about 10 seconds.
No, I think we can show it. It's about 3.4 seconds.
And so turn back to that formula, please. And I think that if you use this formula, it might sense if the difference of shape is changing. But since you just it's just reading about, it's just rotate about 3 to 4 times, there won't be a apparent difference of shape of the ring. So assessing
Sorry, apparent difference of what?
the shape,
Shape.
yeah, the changing of the shape.
You,
Yes, I mean, if you use this formula, and it's talking about a rolling resistance coefficient.
Yes.
And it will, and this coefficient will only changes if the shape of the ring changes. And since you just like, okay.
I think there's something wrong here.
And also in this formula, if I put t inside, there won't be a terminal velocity. Since if I put 1,000 inside, and it's still
You just mentioned before, I knew I had a conversion here.
okay. The next page, please.
This is zero log.
And about t, that formula, mu n into equals to mg.
Yes.
Since we're just talking about friction, so I think it might not use mu n because it stands for the static friction. I think that is still it might use the kinetic friction. Since there's a sliding.
Oh, yeah. So, okay. I know what's the next time is a good suggestion, but I think we should mention here more about the middle here, because as he said that there's a auto sliding, and there's a sliding motion here. So
And in this formula, since you're just talking about the gravity, but the mass unit you use in here is no, the mass is m, but this one is
we
millimeters.
should get a unit during our conversion.
Oh, okay. So this formula was that. And can you turn to the experimental data? And how do you explain the boundary line between them, like 1, 2, 3, 4, 5? What's this line extent?
We use when we are trying this time, we compare the line with the experiment footage. So we can when we are making it, we can clearly see every stage of motion of the ring. So that's why we scale on the boundary for.
I mean, how do you explain the gradient difference between 1, 2, 3, and 4, and 5? Since this gradient seems bigger, and this is smaller. It's the slope. This slope is bigger.
Yes.
So it's smaller. And how do you think the differences between them?
The slope. Yeah, I think because as an initial stage, it's just nice. And it doesn't have a lot of contact points comparing to this. So that might cause it the slope.
And okay. About your parameters, and how do you think it will change if we change the radius of the ring and the rod, since you've only used the same radius in this experiment?
I think if the radius of the ring gets increases, the sliding motion, the first stage will be longer.
Okay, and enough. Summary of discussion by the opponent.
In our discussion, we modified the error on this formula, which is the which that we must use kinetic friction instead of static friction. And also, there are some errors in the formula that if that formula stands, there won't be a terminal velocity. And also, we have clarified some confusions about the data and differences between gradients. And it did a good job on explaining about the theory part. And during our discussion, we discussed the contact point between the differences between one contact point and 2 contact point. And this is the narrow part of my summary.
Questions asked by the reviewer.
And your demonstration right now, why will the ring first fall? Can you explain the reason that why will the ring fall at the first on the top and then go spin? Can you explain? I'm not.
So first we try to spin the ring, but we spin the ring at a horizontal way, so the ring will not have a lot of contact points with the rock. So and then when it falls, because of the spinning, the ring will start to move, changes its position and start to colliding with the ring.
So what about this question? Just like Thomas made a mistake, we didn't just put it down. There must be some angle. So I think there's the angular velocity and angular acceleration between that. So it was like rotated down instead of just drop down. So you mean that you didn't use this method to put the ring down and then drop? I'm sorry, I can't understand your question. Okay. I want to ask you about that. Will the results affect by the weight? The weight increase the washer?
Yes, because it affects the sliding motion. You can see here. The affects the cycle, but if the coefficient, if the friction of the force is the same, it will maybe the distance between the length of the body the terminal velocity to against. So that will be okay.
What about opponent's force? If the washer increase the weight, will the affect the results? I think it will also. In addition, I also think the radius and the height of the ring will also affect this. It will also affect in this experiment. So what about? Can you measure the initial velocity you give to the washer?
No, cannot.
And I also think we can measure it since there's not what kind of way to measure it. I think we can measure it since we didn't spin it out by the machine. We used it by in their experiment they spin the ring down by themselves. Thank you. Here's the problem statement. I think the problem statement was to study the motion of the washer and what determines the terminal velocity. So
First of all is the summary of the and comment of the report. And first of all, for the observation and theory, and the report tell us the study motion, two types of study motion. First is circular motion and the sliding motion. And he also explained the terminal speed. And he also mentioned some equations about moment force, stage friction, and angular velocity. And for the experiment data, we used the chart of the tracker to perform the results. And for the conclusion, I guess is the vibration of the route causes the data to be included. And here's the advantage and suggestions. First, the advantage for the reporter, it has its own opinion about the experiment results. And for the suggestions, the lack of conclusion, the incomplete theory, lack of experiment data, for the lack of the explanation of the phenomena, and put more experiment study. And here's the summary and comment of the opponent. So opponent first starts at the summary of the reporter and the advantage and suggestion, and then the discussion for the structure. And the advantage for the opponent is clear question and catch the mispoints of the reporter, and it is excellent questions for key points, and for it have mentioned the key points of problem statement. And for the suggestions, discuss more about the question of the theory and discuss more variable. And here's the summary and comment of the discussion. First, the question that we get is, the opponent asks that I think the notation of the friction is not correct, because he thinks that is the kinetic friction. But I don't agree with the reporter, because when the rolling motion has no sliding, at the moment the contact points change. And the second question is, what do you think the energy will transform as? And the reporter says potential energy will transform to friction. But I don't agree with the reporter, because the potential energy should be transformed into the kinetic energy of the washer. And for my question, can the initial velocity you give to the ring on the screen be measured? And the opponent and the reporter all both said no. I think the initial velocity will influence the time to reach the terminal velocity, but I think it's true for hard to measure. The second is, will the results affect by the weight of the washer? And the opponent and reporter both said yes. And I think the velocity of the precision will not be affected by the washer's mass, but the translational velocity will be affected. And then is the summary for the next points. First is the contact points, and the second is the different rods he didn't mention. And that's my presentation.
The reporter, please provide a concluding remark.
So I have 3 points to remark. The first is that I forgot to talk about that the number of times we try out the experiment. And for the answer of this question, we tried out a lot of times, but a lot of times it failed, because the reason might be the initial angular velocity is not enough, or either about the vibrating of the rod. So actually, and this refers to the answer of the reviewer. And the reviewer asks, is the initial velocity can be measured? And we say no. And the answer for that is because when we try different times, we use different we try to use different forces to work, but the results are random. And the second point we're going to talk about is between the kinetic friction and static friction. I think this experiment and this problem statement, this question is a big discussion for the whole report, because there are 2 kinds of motions, as I mentioned before in my report. If 2 kinds of motion combined together, the discussion for between kinetic or static is problem. So I think this can be our further experiment too. And that's all for the report. Thank you.
Now it's the time for the viewers' questions, if any?
So I just for question for I noticed that your data also has negative velocity.
Oh,
Right?
oh yes.
Could you explain?
Oh, yes. When the ring starts to landing on the rod, sometimes the angle is not right and it will bump the ring upwards. So like goes down and goes to the other side and bump it upwards. Like in a
Yeah, I know, but does that include in your theory?
Oh no, we didn't expect that to happen.
So,
I think that is,
sorry, component.
actually, I don't think that there will be a force that makes the ring to go upward. But I do agree that if they consider this parameters, they should put it in their theory or modify this.
I agree with that. And at the moment, I think you should put in the theory discussion.
Okay, about the angle between ring, initial angle between ring and the rod. So do you consider that is important to determine the vertical
Do you mean the initial angle?
initial angle?
Oh, but when we try out the experiment, we try out a lot of rings, and when we try to do it in the angle and start to spin it, and that will destroy the structure of the ring. So it's very hard to show, and you will not have a result of the if you have an initial angle, you will not have a result. Yes, we try to demonstrate it, but it all failed because we destroyed all the rings.
All fail, okay. How about the river?
I think that it can show in the theory discussion for the calculation in the initial for the theoretical value, but I think it's hard to demonstration in the experiment.
And as for me, I think it would affect the result, but in the formula they use, there the terminal velocity, I didn't see the parameters which have the angle. So I'm not sure if it will affect, since from the formula there are no parameters about the angle, but
How about your opinion?
as for me, I think it will affect.
The questions? The ratio of the radius of the washer to the radius of rock, does it make a difference?
Yes, definitely. Because if the radius of the ring is too big, there will probably not be a terminal speed. If we have only this length of the rod, if we have a longer rod, maybe we can find out the terminal speed, but we didn't. So I think that is also a variable of this experiment. Yes.
Did you investigate that?
Yeah, we tried a bigger one, but it didn't show any, just false. Just from the start to the end.
What's your opinion?
And I think it will affect, since if the weight, the height is too big, it would affect the inclination angle, and maybe there will be some force in it. So I think it will definitely affect the result.
I think it will affect the results for different frictions or the angular difference.
Okay. Any other questions?
So, your experimental data, your rod is probably 1 meter long. So I just guess that if you make your rod 10 meter long,
Yes.
will you affect your terminal velocity?
I think the terminal velocity. I think the terminal velocity is all because of the friction between the rod, right? So if we have a long
Quick answer, no. Yes or no?
oh yes.
Yes. If the rod is 10 meter long, it's very long.
I think it won't affect the.
I think that.
Okay. Now it's the time to scoring. Start with the reporter. 6, 7, 4, 5, 5. The opponent. 7, 7, 8, 7, 7. Finally, the reviewer. 7, 8, 7, 5, 8. Is there any comments?
I think the vibration of the rod from your student is very important because you feel the rod on the end. But if it's too end, I think
No.
your
This rod on the stable side. We try to
very stable.
Yeah, very stable. And we try to.
Okay, we can discuss.
Okay,